Hello. Okay, we're doing limits at a point today. So when we're trying to find the limit at a point, we're trying to see if we can unambiguously tell you what's happening close to a certain input. So in this first example, we have the limit as x approaches 3 of x cubed minus 5x. So the easiest way to tell what's going on, if we're allowed to, is just to say, well, what's the closest number in the world to 3 would actually literally be 3, right? So can we plug in 3 with no problems? 3 cubed, let's see, 3 cubed minus 5 times 3 would be 27 minus 15, and that's 12. So this one's unambiguous. We know that as we get close to 3 on this particular continuous function, we're going to get very, very close to 12. That's the answer to the problem. How about over here? When we try to stick 0 into this expression, we get 0 minus 5, that's negative 5, over 0 minus 0 plus 4. So again, unambiguous. It's very clear that this rational expression is getting very, very close to negative 5 over 4. How about down here? If we were to replace negative 3 for t, on the numerator we would get negative 27 plus 27, that's 0, over negative 3 plus 3, which is 0. And 0 over 0 is undefined. Okay, this means that we have to do something to this problem in order to make it something we can work with. So I'm going to do some algebra. Let's take the limit as t goes towards negative 3, and in the numerator, I'll factor t plus 3 times t squared minus 3t plus 9 over t plus 3. Algebraically, I can simplify, I can cancel out the t plus 3. And now what would I get if I replaced t with negative 3? If I plug in t as negative 3 now, we would get negative 3 squared, which is 9, minus 3 times negative 3, which is plus another 9, plus another 9, which is 27. And that's again unambiguous. There's no problems there. So what's funny is we're kind of seeing 0 over 0 equals 27, at least in this case, right? That's a funny way of looking at it. Not correct way either, but still kind of funny. Okay, if we were to replace negative 3 into this expression, we'd get 9 minus 18, which is negative 9, plus 9 is 0, over 9 minus 3 is 6, and 6 minus 6 is 0. So again, we're in a do something type stage. So let's do something. Limit as x approaches negative 3. On the top we have x plus 3 squared, and on the bottom we have x plus 3 times x minus 2. So in this case, one of the x plus 3's cancel, so we have a limit as x approaches negative 3 of x plus 3 over x minus 2. And again, let's just try to plug in negative 3. So in this case, we would have 0 over negative 5, and that is unambiguous. That's going to be a 0. Okay, more problems. Let's try this one. Now we have a cubic function over a cubic function, and it is not clear how we could, well, let's plug in 1 first and see if we have to do something or not. 1 plus 1 is 2, 2 minus 5 is negative 3, and then you add 3 is 0. 1 minus 3 is negative 2, plus 2 is 0. So again, it's a do something type of stage. So now with this one, I guess we would have to do some kind of rational roots test, or factoring by grouping's not going to work here. So we're going to have to do something. Now I'm going to use the fact that I'm limiting towards 1. So that means when I stuck 1 into the numerator and 1 into the denominator, in both of those cases, it gave me 0. So that means that 1 is a root of those polynomials, right? Because I stuck in 1 and I got 0. So in order to see what is remaining here, let's write this as the limit as y approaches 1 of y minus 1 multiplied by some quadratic. And on the bottom we have y minus 1 times some other quadratic, right? To see what those are, let's do some synthetic division. 1 into the numerator, 1, 1, negative 5, 3. 1, 1, 2, 2, negative 3, negative 3, 0 would leave me with y squared plus 2y minus 3. And in the denominator, we'd have 1 dividing into the 1, 0, negative 3, 2, which would be 1, 1, 1, 1, negative 2, negative 2, 0. So there we'd be getting a y squared plus a y minus a 2. And let's see if I can just do a little bit more factoring since I'm at this stage anyway. Let's see, limit y goes towards 1 of y minus 1. This one becomes y plus 3 y minus 1. And in the bottom we have y minus 1 times y plus 2 y minus 1. Notice that there is a lot of cancellation from the top to the bottom, leaving us with limit as y goes towards 1, y plus 3 over y plus 2. And now if I just plug in 1, what do I get? 1 plus 3 is 4. 1 plus 2 is 3. And that's fine, right? That's unambiguous, so we're done. Okay, next one. Limit as x approaches 5 from the left of this expression. So if I were to just plug in 5, in the numerator I'd get 5, and in the denominator I would get 0. This is undefined, and this is undefined in the way that it's an asymptote, so it's either plus or minus infinity. And we have to go discover which one of those it is. Okay, to do that, let's think. If I were to stick in a number that was less than 5, a little bit less than 5, the numerator would be positive. And if I were to stick in a number that was a little bit less than 5, like 4.9, 4.9 minus 5 would be negative. Positive divided by negative is negative. And therefore, the answer to this limit is going to be the negative infinity. It was either plus or minus infinity, and we just discovered that it was the negative infinity. Okay, down here in this corner, if I were to replace x for 3, we get 3 over 9 minus 9 is 0. So again, it's undefined, and it's either plus or minus infinity. This one did not specify from the left or the right, so we'll have to do those two cases separately and see what happens. So if I were to do it from the left, the limit as x approaches 3 from the left, well, in that case, we would get, let's go x over x squared minus 9. For this one, if x were a little bit to the left of 3, we would have positive. Down here, you'd have a number left of 3, so it'd be like a 2.9 squared minus 9 is negative. Positive divided by negative is negative. So this answer would be negative infinity. Whereas if we were to do the limit as x approaches 3 from the right of x squared minus 9, this would be plus or minus infinity. Let's go see which one it is. A number a little bit bigger than 3, like 3.01, would make the numerator positive. This would become a number larger than 9, subtracted by 9. That's positive. And a positive divided by a positive is positive. So this would become plus infinity. And therefore, overall, the limit does not exist. For a limit to exist, it has to be the same from both sides. Okay, how about this one? 8 from the left. Okay, 8 plus 8 is 16. 8 squared is 64. 64 minus 64 is 0. So this one is either plus or minus infinity. Let's go discover which one. 8 from the left, so like a 7.9 plus 8 would be positive. 7.9 squared is a little bit less than 64, so if we subtract 64, that'll be negative. And a positive divided by a negative would be negative. So the answer to this one is negative infinity. Moving on to the second page, let's find the limits or explain why they don't exist if they happen to not exist. We are approaching 4 from the left. Numerator is 1, denominator is 4 minus 4, which is 0, and an absolute value is 0. So this is undefined. It is either plus or minus infinity. It's an asymptote undefined. So, is it positive infinity or is it negative infinity? Let's go see. The top is just 1. That's positive. The bottom's an absolute value, So that's simply always positive. And a positive divided by a positive is positive. So this answer is going to be plus infinity. B, stick in 9. 9 minus 9 is 0. Radical of 9 is 3, and 3 minus 3 is 0. So this one's undefined, but it's undefined in the do something stage. So we have to do something. So let's try... I'm going to factor the numerator as a difference of squares, because 9 is 3 squared, x is rad x squared. So I can interpret this as 3 plus rad x times 3 minus rad x over 3 minus rad x. Get some nice cancellation, so we have a limit as x approaches 9 of 3 plus rad x. And again, we will attempt to replace x with 9. This time we're not dividing, so it'll work. Square root of 9 is 3, and 3 plus 3 is 6. This also had the option of multiplying by the conjugate of 3 minus rad x on top and bottom, which would allow you to be able to do some rationalization of a denominator, and the answer will still come out to be 6 at the end. So in other words, it doesn't matter how you do the problem. You can do it in whatever method is most natural for you. Problem 3. Limit as x approaches 0 of this piecewise function. Okay, we want to see what happens when we approach 0, so that means we'll have to do a limit from the left and a limit from the right. If we approach g of x as x approaches 0 from the left, numbers that are less than 0, we would be following that rule. That rule is x minus 1, and as x approaches 0, could I just plug in 0? Yes, I can. I get negative 1. If we approach 0 from the right, so we're a tad more than 0, we're following this rule, which is x squared plus 1. And if I replace x with 0 there, I get 1. Notice these are different, so that means our limit does not exist. From the left, it's negative 1. From the right, it's positive 1. And this is ambiguous. What side am I coming in from? That depends, that affects my answer. So we're not allowed to, this one is an does not exist limit because it's different from either side. How about here? X approaches 1. So again, limit as x approaches 1 from the left. A little bit less than 1 would mean we're smack dab in the middle of this interval, so that'd be an x squared plus 1. 1 squared is 1, 1 plus 1 is 2. Limit as x approaches 1 plus, still in this interval, x squared plus 1, 2. These are the same, so overall we can say the limit is 2. Unambiguous, right? From the left and from the right, you're getting the same output. Final example for this little part is x approaching 2. So if we do a limit as x approaches 2 from the left, we would be on this interval. 2 squared is 4, 4 plus 1 is 5. And if we approached 2 from the right, we'd be bigger than 2, so we'd be following this rule. Negative 2x plus 9, and if I were to stick in 2, negative 2 times 2 is 4, negative 4, and negative 4 plus 9 is also 5. So this one also, the limit does exist, because it is unambiguous. From both sides, the two pieces were the same. So this one, different. This one, the same, but it was just the same rule. And this one was the same, even though they were following different rules. Okay, next example, I think that's our last one for today, is evaluate this fancy limit. So to do this one, I'm going to do some, well, let's first stick in 0 and see what we get. 0 plus 9 is 9, square root of 9 is 3, 3 minus 3 is 0, over 0. So this is a do something, we got to go and do something. And what I'll choose to do is multiply by the conjugate. So I will rationalize the numerator. Radical x squared plus 9 minus 3x multiply by x squared plus 9's radical plus 3. Radical x squared plus 9 plus 3. So what does this do for me? It means that in the numerator I'll get this quantity squared, and the square root squared is just the quantity, so it's x squared plus 9, minus 3 times 3, which is 9, and that's all over x, multiplied by radical of x squared plus 9 plus 3. 9 minus 9 cancels out nicely. X and x cancel out nicely. So we get a limit as x approaches 0 of x over radical x squared plus 9 plus 3. So now plug in numbers close to 0, or effectively 0 here, and we get 0 over radical 9 is still 3. 3 plus 3 is 6. And of course, 0 over 6 is equal to 0.